What we see here is a scene of New York, and I want you to look at all of the people. Look at all of the statistics that are all around you in this video. See the cars and the trees and the buildings. We might have average weights. And look at this nice guy. He sure is friendly. Maybe there's an average friendly quotient here. A FedEx truck, maybe an average time that it takes to make a delivery. If we were to pick out one of these individuals just off the cuff and look at them, we might want to compare them in some way to the average of all of the rest of the population. Take that little black car. What do you think the cost of that car is in regard to the average cost of all cars? Welcome to this lesson about z-scores, which is entitled Z-Score in the Land of Nerd. What is it anyway? Brought to you by Dr. Dog. Do you remember the previous picture that we had when we walked up and said 150, and you understood that that raw data had to have some relevance to a mean and a standard deviation in order to have meaning? We took this raw data of 150 and drew a picture of the mean and the standard deviations of the distribution and found that this data point lay 2.5 standard deviations above the mean. Well, one of the things we might ask ourselves is how do we convert any raw data point so that we can discuss it in terms of mu and sigma, remembering that mu is the mean and sigma is the standard deviation. Now, in that last one, we were able to look at the picture. Well, you know, that's good and that's bad. I love the picture, It's easy to read that picture, but for some data, the picture is just not very nice. For this, we're going to need a name and a formula. We're going to need something to refer to how many standard deviations a data point lies above or below the mean. We will call that a z-score. The z-score is the number of standard deviations a raw data point lies above or below the mean. Now, I want you to look at how much you've learned. You know what mean is, don't you? That's the numerical average. The standard deviation, you also know, that's the average distance from the mean, which is a measure of the scatter of the data. A raw data point is one value. So a z-score takes a one value raw data point, examines that raw data point and how many standard deviations above or below the mean that data point lies. Pretty interesting. In our previous illustration, the z-score for 150 was 2.5. We were able to look at the picture and determine that our raw data point lay 2.5 standard deviations above the mean. Do you remember this marvelous picture that we had here? In this picture, we have a mean of 100, we have standard deviation of 20, and we had a raw data point of 150. Our raw data point lies 2.5 standard deviations above the mean. If we use a z-score to reference the number of standard deviations a data point lies above or below the mean, then someone could say this raw data point has a z-score of 2.5, and that would immediately tell us that that data point lies 2.5 standard deviations above the mean. Now that one was easy because we had a real nice, pretty little picture. What is the z-score of 92? You see, things get a little bit more complicated. When I ask you what is the z-score, I'm asking you how many standard deviations above or below the mean does the data point 92 lie? In this case, the picture doesn't work well. We actually need a formula. Well, what we're looking for is a z-score for 92. That means how many standard deviations above or below the mean does 92 lie? To calculate this z-score, we're going to need to take the distance so that 92 is from the mean and divide it by one standard deviation, so that it tells us how many standard deviations above or below the mean that this data point lies. Well, let's look at this thing just a minute. What does the formula look like when we do this? What is our formula? How might we take this formula and use it? Well, here it is, my friends, here it is. The z-score for 92 is equal to 92 minus mu divided by sigma. Why 92 minus mu? 92 minus mu is the distance that 92 lies from the mean. Dividing it by sigma takes that distance, that raw distance, and divides it by how long a standard deviation is, so that it tells us exactly how many standard deviations the raw data point of 92 lies from the mean. Here we go. As we plug in our values, our z for 92 is 92 minus the mean divided by the standard deviation. 92 minus 100 over 20. 92 minus 100 is negative 8. Now, bear with me. 92 minus 100 is negative 8. So we now know that the z of 92 is equal to negative 8 divided by 20. The z-score for 92 is negative 0.4. Now look at our picture again. Our formula tells us that the z-score of 92 is negative 0.4. So that little data point of 92 that the arrow is pointing to has a z-score of negative 0.4. If somebody walked up and said, well, our raw data point has a z-score of negative 0.4, you could immediately envision that that z-score is below the mean, and it's roughly it is actually 4/10 of a unit below the mean, 4/10 of a standard deviation. Those z-scores that lay below the mean will be negative. Those z-scores that lie above the mean are positive. Now, let's review just a second. Look at all the wonderful things that you've learned. What is a population? What is a sample? I mean, differential statistics, inferential statistics, nominal, ordinal, interval, ratio. Man, you just blowing and going with this. Random means every data point has an equal opportunity of being selected. You're learning. Now you know what a mean is. It is a numerical average. If it's mu, it's the population. If it's x bar, then it is the sample. We're able to do some things where we know what standard deviation is. We know mu and standard deviation. Standard deviation is the average distance from the mean. Most of the data will cluster close to the mean. So the more standard deviations we get away from the mean in either direction, the less of them there will be. We now know mean and standard deviation. We understand that variance is just the standard deviation squared, or the standard deviation is the square root of the variance. So we know mean, standard deviation. We also know z-score, because the z-score tells us how many standard deviations above or below the mean that a data point really is. Guys, you're catching on quick. This is getting to be fun.